In this section, we're going to be covering volumes, and in particular, we're going to use solids of revolution to find volumes. So volumes is a topic that is covered more in depth in Calc 3, but we have some tools now that we can use to find volumes in special cases. So to start with, let's develop our tool. So let's picture a 3D object along some axis. So let's say the x-axis for now. And let's assume we want to find this volume. First, let's try and approximate our volume similar to how we did with areas in previous sections, where we're gonna break our object into simpler pieces and approximate the volume with simpler pieces. So maybe the volume of this object is hard to find because it has this gentle slope that it's constantly the width of this object's constantly changing. But I could approximate it with these cylinders, right? I could break my object up into cylinders, and okay, I only have the width of this cylinder is constant on this piece and constant on this piece, and this object is an approximation to this object. So this volume that's easy to find should be an approximation to my original object's volume. So let's first talk about this object. What are the volumes of these individual cylinders? Well, the volume of a cylinder is pi r squared times L, where pi r squared is the the surface area of these cross sections. So if I like take a slice of this cylinder, that would give me a circle, right? And the area of that circle would be pi r squared, where r is the radius. And then I would multiply that by the length of the cylinder if it's lying horizontally, or we could also say that the length is that letter L is the height of a cylinder if it's like a vertical cylinder. So the volume of each individual cylinder should be pi r squared times L. Okay. So let's figure out what L is. So if I break my object up into pieces like this, where I have x1 right here and x2, and so my first cylinder is from the points x1 to x2, and then my second cylinder is from x2 to x3. Okay, then I can say that the length for the first cylinder is x2 minus x1, and the length for the second cylinder is x3 minus x2. Let's call the area of the cross sections for this first cylinder, let's call those AX1. Okay, so I take a cross section of this cylinder, and it's going to have surface area AX1. And then if I take a cross section for this second cylinder, it's going to have area AX2. So the area, or excuse me, the volume for the first cylinder would be AX1 times x2 minus x1. Okay, so breaking this down, what is this AX1? It's pi r squared, where r is the radius of this first cylinder. Okay, and then x2 minus x1, well, that's the L, the length of the first cylinder. And then I have something similar for this second piece, this AX2, well, that's pi r squared, well, where r is now the radius of the bigger cylinder. And then this x3 minus x2 is the length of this cylinder. So my approximation to the volume of my object looks like this. Okay, AX1 times x2 minus x1 plus AX2 times x3 minus x2. And we can make our approximation better and better by making more and more slices of our object. So here in this approximation, I broke my original object into two pieces, right? If I break my object into more and more pieces, I'm going to get a better and better approximation, okay? So let's say I break it into n different cylinders, okay? And I write the area of each individual cylinder like so. Okay. Now, I just abbreviate that with this shorthand where I have this sigma notation, this summation notation. So my approximation to the volume of the object is the sum from 1 to n of AXI times delta xi. Now this should be starting to look familiar. This is very similar to how we built up our technique of integration, right? We approximated our area with rectangles, and then we took a limit of this type of sum as our delta xi's got smaller and smaller and smaller, and we ended up with the integral, right? So we're getting something very similar here. We take more and more uh, slices of this object. We make these cylinders thinner and thinner and thinner. And as the width of these, or the length of these cylinders goes to 0, our sum approaches this integral. It becomes an integral. So the summation sign is going to become an integral sign from a to b. My AXI is just going to become AX. And then my delta XI becomes DX. Okay. So now let's recap what we have here. This AX is going to be the cross sections, the surface area of my cross sections. Okay, so going back up to this original object, okay, I'm going to consider the cross sections of my object at each x. And these cross sections have area, right? And that area changes depending on x, right? If I'm looking at this cross section, that has some surface area. And then if I move out this way to this cross section, well, that's going to have a slightly bigger surface area, right? So this surface area depends on x, which is why we write it as a function of x, this capital A of x. Okay, so that's what this AX is. And then we're integrating that function along the length of my object. And that should give me the volume. Okay, so how I would think about this is, once again, going back up to my original object. I'm going to take slices. Oh, excuse me. I'm going to take slices of my object. Okay, so I'm taking my cross sections down my object, and if I integrate those cross sections, the areas of those cross sections, it's like I'm adding up all the cross sections, the areas of the cross sections, and that should give me my volume. So that's the general idea of what's going on. Let's go ahead and summarize it. In summary, we have an object along some line. It's usually going to be an X or a Y axis, but not actually, maybe half the time it's going to be an axis. We're going to deal with a lot of problems where our object is centered off axis. If we can figure out the areas of our cross sections, we can integrate those areas to get our volume. Okay, so I'm going to refer to the area of these cross sections as AX or AY. Okay, you might be asking why it's in terms of X or Y. We'll deal with that later. But if we integrate our area function along our object, we're going to end up with volume. So back to our original object. I have this object, and this little square is like I'm taking a slice of it, and it has a cross section that looks like this. If I integrate those cross sections along my object, I'm going to end up with my volume. Okay, so we can write that formally like this. We're saying the volume is equal to the integral from a to b of ax dx if I'm integrating along the x-axis. So a would be here and b would be here. Or if we're doing everything in terms of y, it would be ay dy. Okay, so what do I mean by doing things in terms of y? Well, if I have an object along a horizontal line. Okay, I'm going to integrate that along the horizontal line in terms of x. But I can also do this process for an object along a vertical line. So if I had an object that was like this, kind of along the y-axis, I could integrate along this vertical line, okay, and get the volume as well. But if I was integrating along a vertical line, I would want to do everything in terms of y. So my integral would look like that. I would integrate my area function ay in terms of y. We'll cover that in more detail by the end of the video. So that's the general case, and we should have one problem on the homework where we have to use this general idea of finding the volume. I'll cover that more in the problem video. It's kind of a pain, and I'll help you through it. Most of what we're going to be doing is going to be this special case of the solids of revolution. Okay, so what does this mean? We're going to start with some region in the plane. So think of a 2D object, starting maybe we could consider this object. And then we're going to rotate it or revolve it around some line. Okay, so let's say that we're starting with this starred region and we're told to rotate around the y-axis. That would give us a 3D object, right? So picture taking this region and rotating it around the y-axis. It goes down into the screen and around and back and through, and we end up with this 3D object that's kind of like a vase or a ice cream cone. You know, it's however you want to describe it. We rotate around the y-axis and we get this 3D object. So that's what we mean by solids of revolution. We're starting with a 2D object, and then we rotate it or revolve it around some line, and we end up with a 3D object. These solids of revolution are nice because they give us nice formulas for the volumes. Since we're rotating in a circle, these cross sections are naturally going to be circles. Okay, so starting with this region here, the starred region again, I rotate it, and then look at the cross sections. Let's take a slice like this and kind of lay it flat on the page. What would that cross section look like? It would be a circle, right? So all these areas of our cross sections are going to be the areas of circles, basically. But we're going to have two cases, actually. So if it's a solid circle, well, we could call it a disk. But that cross section might have a hole in it, in which case it's going to look like a washer. Okay. So when we take our cross sections, there's going to be two possibilities. It's either going to be a solid cross section, okay, which we'll call a disk, or it's going to be a cross section maybe with a hole in it, which we'll call a washer. Okay. Let's start with an example for the disks. So consider the region enclosed by the curves y equals square root of x equals 4, which is just a vertical line, and y equals 0, which is a horizontal line. Find the volume when we take that region and rotate it around. Oh, I've stated this poorly. There, fixed. So let's start with the region y equals square root of x, the region bounded by y equals square root of x equals 4, and y equals 0. And then let's find the volume of the object we obtain by rotating that region around the x-axis. Okay. So as a first step, let's draw our initial region. Okay, so y equals square root of x is this curve here. And then y equals 0 would just be that x-axis. Okay, so we're using that as a bound. And then we're using x equals 4, this little dotted line here, as a bound. Okay, so when I consider the region enclosed by those three conditions, I get this shaded region here. Okay, now let's take that region and rotate it around the x-axis, and that's going to take this 2D object and turn it into a 3D object, right? So picture what we would get when we rotate this around the x-axis. It would be this horizontal cone, this cone kind of lying on its side. So this is the volume of the object. This is the object whose volume we want to find. So to do that, we need, what's our formula going to be? It's going to be a of x dx, integral of a of x dx. So I need to find this ax, the area of my cross section. So if I take a slice down my object, what's the area of that cross section going to be? Okay, so let's picture these cross sections. I take a slice through my object and I'm going to lay it flat on the page. That's what you're seeing in this square here. I kind of rotate it and lay it flat on the page. So it's going to be a solid object, right? There's no empty space in this object. It's a solid object. So I expect my cross section to be a disk. So what's the area of this disk? Well, the area of a disk or a circle is just pi r squared, right? So my area is going to be pi r squared. What is the radius of this cross section? Well, that depends on x, right? If I'm at this x here, I have this radius, and my radius is increasing as I move along my object. So my radius depends on x. Now let's examine this radius, okay? The radius of this cross section is this yellow line, right? It's the distance from here, the x-axis, up until this point here, okay? So what is that distance? Well, note that our radius ends right on that curve, right? It ends on the edge of our object. And remember that boundary is formed by this curve. What was this curve? It was y equals square root of x, okay? So that radius is the y coordinate of this point, right? The distance from here to here, that's just the y coordinate of whatever point is on that boundary. Okay, so what is that y coordinate? Well, we know that y coordinate is given by this equation, y equals square root of x. And that's what we're stating here. The distance is the y coordinate of the point on the curve, which is given by the equation f of x. In our case here, f of x is square root of x. So the radius is going to be square root of x, okay? So plugging that radius into our formula for the area of the cross section, we have that the area at each x is pi times square root of x squared. So the square and the square root cancel, and I'm left with the area at each x is just pi times x. Okay, so now I have my area function. Let's try and write my integral formula again. Okay, my volume of my object should be the integral from a to b of ax dx. So we've determined that a of x is given by the term here, pi times x. Okay, what are my bounds? Where do I want to integrate? I want to integrate along my object. So going back up to my object, okay, where's my object begin? It begins here at this point x equals 0, and it goes until this point x equals 4. So those should be my bounds of my integral. So my volume should be given by the integral from 0 to 4 of pi x dx. So the last step is just integrating. Okay, I take the antiderivative and I get pi x squared over 2, and then I evaluate that from 0 to 4, and I get the answer 8 pi. So that's the volume of my object. If you're having a little trouble following the steps, I'm going to lay out all the steps towards the end, so you have a step-by-step guide on how to tackle these problems. I'm just giving you some examples right now. Now let's look at an example of a washer problem. So to make clear the difference between a disk and a washer, let's use the same exact region as in the previous problem. So let's use the same curves, y equals square root of x equals 0, and x equals 4. But this time, instead of rotating around the x-axis, let's rotate around the horizontal line y equals -1. Okay, so I'm starting with the same region, but instead of rotating around here, I'm actually going to rotate around this. Okay. So what's my 3D object going to look like? Try and picture it first. Okay. Hopefully you've done that. And behold my masterpiece. I'm very proud of this drawing. I am terrible at drawing 3D stuff, so I think this one turned out pretty well. So we get this 3D object. Again, it's a cone, but instead of being a solid cone, if you can interpret my drawing correctly, there's this cylinder of empty space in the middle of my object. Okay, so this kind of white shaded region, that's the cylinder, the end of a cylinder, that's all empty space. So think of it as vacuum in there. Okay, so with that in mind, what do the cross sections look like? Okay, so I take a slice of my object and lay it flat on the page, and it's got a cross section that looks like this. So it's still circular, but there's this, oh, there's this empty space in the middle. Okay, so that white area is just empty space. Okay, so what is the area of this cross section? It's still going to be based around the areas of circles, but let's see how I deal with that. It's not just pi r squared, right? I can't just do pi r squared because that would give me the area of the entire circle. I need to take out that middle piece somehow. So if I can figure out what the outer radius and inner radius are, meaning, let's see, what do I mean by outer radius? By outer radius, I mean the distance from the center to this outer edge. If I can figure what that is and find the area of that circle, pi r(o) squared, we'll call the outer radius r(o). If I take pi r(o) squared and subtract pi ri squared, where ri is this inner radius, that should give me the area of the washer, right? I find the area of the entire object, and then I subtract away this area, and that should give me the area of the washer. Okay, so the washer has this formula, pi r(o) squared minus pi ri squared. Okay, now I need to find the outer radius and inner radius for each cross section. All right, so the cross sections look like this. Let's see if I've got a, okay, so the outer radius and inner radius really depend on where on the object I am, right? The inner radius in this case is constant. This cylinder of empty space is just the same width throughout, right? It's just the same as we move along our object. So that maybe the outer radius is constant, but this, or excuse me, the inner radius is constant, but this outer radius, which is coming from this curve here, that's changing, okay? So I've kind of drawn my inner radius with these yellow lines and my outer radius with the blue lines, okay? So let's talk about the inner radius first. The inner radius is going to be the distance from this line, the line we're rotating around, which is y equals -1, to this line here, which is the x-axis. So what is that distance? Well, that's always 1. What about the outer radius? Again, I'm measuring the distance from this line, y equals -1, but now I'm measuring to this outer curve, okay? So what is that distance? Well, the distance, let's look at this one right here. The distance from do green. The distance from here to here, all right, the distance from my curve to the x-axis, that's just the y-coordinate of this curve, right? But then I'm not stopping there. I'm measuring the distance a bit further down into that down to the line I'm rotating around. So I need my y-coordinate, which is that distance, plus 1. Okay. So my outer radius is the distance from the original curve, y equals square root of x, to the line y equals -1. So to reiterate, we know that the distance from the curve to the x-axis is square root of x, but now we're going 1 unit further down to the line y equals -1. So that outer radius should be square root of x plus 1. Okay, so that's the kind of logic we're using, and I'll give you a tool to help maybe more methodically do this. This is the rule I've written out for calculating these outer radiuses and inner radiuses. So this is my explanation of how we're finding these this radius. This can be used for outer radius, inner radius, or radius of a washer. It doesn't matter. It's all based around the boundary of our object that we're looking at and the line we're rotating around. Okay, so look at this line here. I have r equals boundary minus line rotated around. Okay, so let's use a new page for a moment. We'll go back to that page in just a second. Okay, let's say I have a function here. I've rotated around this line in the middle, and I get this sort of object. Okay, and it doesn't matter where this object is. Maybe this is the x-axis. Maybe it's not. Maybe it's the line y equals -4. It doesn't matter. What is this distance, this radius, right? It's always going to be this y-coordinate, the y-coordinate of my boundary, minus the y-coordinate on this line, okay? So let's say that this is the x-axis for a moment. Say this is the x-axis, okay? Well, it would be the y-coordinate of my curve minus the y-coordinate on that x-axis. Well, the y-coordinate on the x-axis is just 0, right? And then let's say this curve is f of x, okay? So it would be f of x minus 0, okay? That would be my radius for all these points, right? Let's say instead, let's use this same object. Let's say instead of the x-axis, it was the line, the horizontal line, y equals -3, okay? Again, this curve is fx. Well, then my radius would be the distance from f of x to y equals -3. So it would be this y-coordinate minus this y-coordinate. Well, this y-coordinate here is given by the function fx, and then I subtract away -3, which becomes f of x plus 3. Okay. So that's what we've done for this outer radius, right? We're measuring the outer radius. It's a little busy. Let's clean this up a bit. Okay. So let's look at this outer radius here in blue. We have our y-coordinate at this point on our curve. Okay, well, what is that y-coordinate? It's just given by square root of x at this value of x. And then we're measuring from this y-coordinate here down to this y-coordinate here. Well, this y-coordinate is at -1, so we have square root of x minus -1, which is square root of x plus 1. Okay. So back to this guideline. Now we're just kind of reiterating. Okay, so in general, we have the radius is going to be given by boundary minus the line we rotate around. We're always measuring our radius to the line we rotate around, not necessarily to the x-axis or y-axis. It's always measured to the line we've rotated around. Okay, so in our previous example, once again, our inner radius, for our inner radius, it was always 0 minus -1, so it's always equal to +1. For our outer radius, it was square root of x minus -1, which gave us square root of x plus 1. Okay, so now plugging these radiuses into our radii, I guess that's the correct plural of radius. So plugging these radii into our formula for the area of our cross sections, we have the area of cross section at x, a of x, is equal to pi times rho squared minus pi ri squared. And we know rho is equal to this, ri is equal to this. So after plugging those in and simplifying, I should end up with this expression for ax. A of x equals pi times x plus 2 squared root of x. Okay. Now let's plug this a of x into our integral. And where am I integrating? Looking back at my original object. Okay, I'm integrating from here along my object to here. Okay, this point is at 0. And then my object stops at x equals 4. So I integrate from 0 to 4, pi x plus 2 squared root of x dx. And the rest is just integrating. Okay, so find the antiderivative and check my work. Okay, but I believe it should be pi times 56 over 3 as our final answer. Okay, so now here we are at the steps. So I've written out the steps formally for finding these volumes of revolution. Okay, so these are the steps I would follow. For this, do what you need to do. I'm not saying all of these steps are required when you're showing your work on tests and things like that. That'll be somewhat up to you, but I would do these. These are the steps I think are necessary to be thorough in finding our answers. So I would do these. So start by drawing the region. They give you the 2D region. Okay, so they're going to give you a bunch of curves. They're going to give you an area enclosed by these curves in the plane in 2D. So draw that region, and then also rotate that around the line they tell you to get that 3D object, and try and sketch that 3D object. Okay, and I have some guidelines here that might not make sense right now, but they will in a moment. Remember that we said, let's see, we could rotate our object around a horizontal line, or we could also do this for objects rotated around a vertical line. Okay. Well, it turns out that when we rotate around a horizontal line, okay, so when I have an object rotated around a horizontal line, I'm going to do everything in terms of x. My integral is going to be in terms of x, and so on. And if I rotate around a vertical line, I'm going to do everything in terms of y. I'm going to integrate in terms of y. We'll see that more later, but for now, just memorize this rule. If we rotate around a horizontal line, everything's in terms of x. If we rotate around a vertical line, everything's in terms of y. Our next step should be determine what our cross sections look like. Are we dealing with discs or washers? Step 4, measure the radius / radii from the original curve to the line we rotated around. Okay, so remember we're starting with a 2D object, boom, and then we're rotating around some line. So the radius should be measured from our curve, that curve, the original curves were given, to that line we're rotating around. Okay, so once we find this radius or these radii, we have enough information to find our area functions. Okay, so for disks, it's going to look like this. Okay, so if we've rotated around a horizontal line, everything's in terms of x, and we have a of x equals pi rx squared, where this rx is just our radius at each x. Okay, if we've done everything, if we've rotated around a vertical line, our stuff's going to look like this. Okay, so that's for disk, and then we have something similar for washer. Okay. Next, we should find the bounds of integration. So where we're rotating, where our object exists, where if our object exists like this, it's rotated around a horizontal line. I want to integrate from here to here. Okay. So we want to integrate along our object. Sometimes we got to figure out what those bounds are. All right, and that's enough information to form our integral, and we know that the volume is going to be equal to our integral from a to b, a of x dx. Again, that's if we've rotated around a horizontal line, and this is for vertical. Okay, and then we just integrate. So the hard part of this is not the integration, it's definitely setting everything up. Okay. So now let's see a case where we've rotated around a vertical line. Let's see how things change. And I'll do some examples following these steps so you can see these steps applied methodically. So in all the examples so far, we rotated around a horizontal line and found the volume by integrating in terms of x. But as I said before, we may be told to rotate around a vertical line instead. Then the process is pretty much the exact same, but we're going to integrate in terms of y. So let's see that in action. Let's say we're given the initial 2D region bounded by the curves y squared equals x and x equals 2y. And we want to find the volume when we rotate this region around the y-axis. Okay. So step one, drawing our 2D region. So this is kind of stuff kind of carried over from section 6.1. We got to find that initial region, right? We got to find that region enclosed. Okay. So this is the curve x equals 2y, which is the same thing as y equals x over 2. Okay. And then this sideways parabola would be x equals y squared. Okay. So there's only one region enclosed by those curves. It's that yellow shaded region. Okay, so let's just erase all the extraneous information and we get this thing, and we want to rotate it around the y-axis. So picture what that would look like in your mind. Okay. And now to see the result, I'll scroll down. So we're going to get some 3D object like this. So it's a cone, but notice these dotted lines in the interior of our object. Those are like the inner walls of our object. So our object's not solid, right? We got a lot of empty space here in the middle. Okay, our object really only exists in that region rotated around. Okay, so it's kind of like a bowl. Okay, it's got a lot of empty space in it. So that brings us to step 3, finding these cross sections. Okay, so it's blank right now, so let's go ahead and think about what happens when I take a slice horizontally. Okay, I take a slice and consider that cross section. Okay, what's that cross section going to look like? I'm going to lay it flat on the page. Okay, it's going to be a washer. Okay, sorry for my horrible washer. So it's not a solid object. It's got some empty space in the middle. Okay, and in fact, it's going to be mostly empty space, right? Okay, so we know the cross sections are going to be washers. Next step is finding these radii, the outer radius, inner radius. Okay, so we're going to measure the distance from the line we rotated around, which is the y-axis, and then to our object. Okay, so our outer radius in yellow is the distance you see there. Okay, so what is that distance? It's going to be Now that we're doing everything in terms of x, okay, just a quick sketch of what's going on, okay. This outer radius measured from the y coordinate to this curve, okay. What's that radius? Well, let's see, instead of the, in the previous problems, it was the y coordinate, right? But since we've rotated around a vertical line and we're doing everything in terms of y, okay, this distance is going to be a function of y. Okay, what functions of y are we dealing with? We got y equals, or excuse me, x equals y squared and x equals 2y. So this distance is given by the curve x equals 2y, right? Sorry, it's so busy in there. Okay, so that distance is x equals 2y. Okay, which I've stated here. So RO is equal to 2y. What's the inner radius? Well, that's this blue line measured from here to here. Okay, and that's given by the curve, that x coordinate is given by the curve y squared. So our inner radius should be Ri equals y squared. Okay, so we have our radii, we have our outer radius and inner radius. So those we can plug into our formula to find our area of our cross sections in terms of y. So we have the area AY equals pi times 2y squared minus pi times y squared. Simplifying those, we have the AY is equal to pi times 4y squared minus y to the fourth. So that's going to be our area function. Okay. Now let's find our bounds of integration. So if I'm looking at this left side, this 3D object, where do I want to integrate from? Well, I want to integrate along the y-axis vertically, starting at this blue dot down here at the bottom and going towards here. So that it might be a little unclear what points these are looking at our 3D image. So let's go back to our 2D image, right? This is the region I'm starting with, and I'm rotating that. But just look at this 2D image. I'm essentially integrating along this y-axis, right? From here to here, from this blue dot to this blue dot. So what are these points? Well, this blue dot we can see is at the origin, but more generally, it's where these two curves intersect, right? It's where these curves intersect here. And then we integrate until we get to this blue dot, which is where these curves intersect again, okay? Why is that? Because this 3D object we're making is derived from this 2D shape, right? Okay. So this 2D shape starts where these curves intersect and it ends where these curves intersect because we were dealing with a curve, a region enclosed by these two curves. Okay. So what are these points? How do I find these points? Well, I set my two curves equal to each other. I set 2y equal to y squared, and I solve for y. And again, I want to do this by moving everything to one side of the equal sign and solving. Okay, so I wouldn't want to just divide by y. That wouldn't give me the full picture. So I move everything to one side of the equal sign and factor or use quadratic formula. And what do I get? I get 0 equals y squared minus 2y. I factor that to y times y minus 2. And so my solutions to that are y equals 0 and y equals positive 2. So these are going to be the points where our curve intersects. So it intersects at y equals 0, this point right here. And then it intersects at y equals 2. So those are going to be my bounds of integration. And now I have all the information I need to form my integral. It's going to be the integral from 0 to 2, pi times 4y squared minus y to the fourth dy. and then everything else is just integrating. Okay, so you can check this on your own. But it should all work out to 64 pi over 15. Okay, that's all I have for the general outline of the material. This stuff's pretty complicated. 6.2 and 6.3. People often have trouble forming these, setting up these integrals, so don't feel too freaked out if it's a little hard. I will do a problem video for this section where I solve a couple of each type of situation, disks and washers, integrating in terms of X and Y and so on. So I'll try and cover all bases with that. So check that out if you're having problems. That'll be up in the next couple days.